So there were two definitions. The first was that the difference of potential, the changing potential energy of a system is equals to negative of work done by the system itself. And why it is minus? Because of the very intuitive way of understanding the work. So to do work, we need some energy. And if a system is doing some work, then the energy must be derived from the system itself. And therefore, it will turn out to be the reduction in the value stored. That is why we have the definition. The second definition which I gave, that the changing potential energy is equals to positive work done by external with condition applied that the work must be carried out slowly. So the process must be slow. So the process should be slow enough such that the delta K is. So if the delta K we are not making any changes to kinetic energy, then what we can say that the work will be consumed as a true change in the potential. So these are two definitions, and based on the two definitions we proceed. So we have seen the potential energy formula for various gases. For gravitational, we have mgh. Now, how to calculate the potential energy change, that is delta U, while solving the problem of lifting the object. So for gravitational potential energy, we have a concept of a reference. So let's say we are doing some work by taking an object from somewhere to somewhere. So let's say the object is somewhere here at the bottom of this, and you want to take it somewhere here. This is the place where you want it to be, and the height with which you want to carry out is let's call it uh, h. Now this is the path you're taking. Let's say you are taking from bottom to the top, which is h height above. And now what we do is we can create something called reference line. So I'm calling the bottom as the reference, but I can take any other point as reference. So let me call this also as a reference, and let me call reference number 2. Let's name it reference. And then I choose some random referencing level, which I don't know where to take. So I'm just naming it at a random height, and I'm calling this random height as y. So it could be anything, and I'm calling the reference number. So how do we calculate the delta U? So now, as I have discussed, that the potential of reference we take as 0. So as a thumb rule, P at reference, we assign 0 potential energy. And why it is so? Because eventually our goal is to establish the change. So no matter what is the exact value presently and what is the exact value finally, the change will be independent of the reference station. So by assigning the reference potential as 0, we can efficiently calculate the change in potential. Now the other rules are like potential energy above the reference we take positive. And the last rule is potential energy below reference, we take negative. So that is the case, the potential energy above and below, we do this calculation. So let's calculate the delta U for reference 1. So delta U for reference 1. By definition, delta U is always final minus initial. So tell me guys, what is the final position? Is it above the reference or below the reference or on the reference?
Above the reference.
And how much it is? You can see it's H. So we write as mg. That's it. And what is the initial value? So initially the ball was at reference 1 itself, right?
Yes.
And therefore this must be.
0.
So you can see that the delta U turns out to be mgh. Always remember the mgh represents the delta U of system, not of block. I mean, not of the ball itself. So mgh is not the potential energy associated with the ball, rather it is the potential energy change of the system called ball earth system. So this is the change in P of earth ball system. Now the question is why I have included the earth here also. The reason is you must include all the masses which interact, because I am defining the potential energy of earth and ball, so I must include the earth, because I cannot define potential of one individual. Potential is, I mean, the potential energy is defined for the system, for the interacting masses or charges, not for the isolated parts. Okay. So this is the answer for reference one. So let's change the reference and see how we can still calculate the answer. So let's calculate the delta U for reference 2. Now you have to ignore the reference 1 and reference 3. So as per the reference 2, what is the final position? What is the final position? So finally, where is the ball?
Sir, above the reference line.
Now I'm asking, now the definition should be as per reference 2. So as per reference 2, where is the position of ball finally? Now reference 2
Oh,
is
on the
your
same
reference.
line. Sorry. On the same.
So it is on the reference. So the final potential energy must be
0.
okay. Next. So what is the initial?
Minus mgh.
Minus. Because it is below the reference, and therefore the delta U will be final minus initial. So no matter how you choose the reference, you'll get the same answer. And proceeding the same fashion, we can also conclude.
Mgh minus 1.
Yeah, correct. So for reference 3, can you tell me what is the U final?
Mgh minus 1.
Very good. And what is U initial?
0.
What is initial?
So no. Mgy.
Mg.
Y.
Plus or minus?
Sir, no. It's 0.
See,
It's on the
your reference is here. This is your reference. So you must answer in terms of this new reference, not the previous reference. So the final is mg h minus y because you are above the reference by h minus y. What is the initial value? Tell me.
mgy.
It is below the reference. Can you see that?
minus mgy.
Minus m. So the potential in the beginning is below the reference, so it is minus mgy, and the finally it is above the above the reference by the value h minus y. So the answer is plus mg h minus y. And if you do the calculation of delta u, again it turns out to be mgh. Now what I'm trying to demonstrate here is that no matter where you choose the reference, because our purpose is to calculate the change. So the change does not depend on the reference. It could be anywhere and still it will give you the same answer. Now by the proper choice of reference, your answer or your way of writing will change. So you may interpret the answer differently. So that's totally okay because the way you choose the reference will change the initial and final value, but it will never change the difference, that is the delta U. So what we need to realize that the calculation of change in potential remains independent of what? A reference line. Okay. Now, what kind of question we can expect? As I said, potential is another way of talking about a work. So if you want to talk about the work, that's fine. If you don't want to talk about the work, then you have to go through the potential definition. Okay. So let's say we have a table. Maybe we can take this pulley question first. So let me take a pulley. So we have a pulley, and now we have a chain which is hanging from the pulley. So it is difficult to draw, but I will try to. Okay. So I can draw something like this. That's the only option I have. Um, okay, this is better. So you can see here, a rope is passing over a pulley. The rope is passing over pulley. So the rope is having some length. You can say length is L. So on both sides, it is hanging, let's say, equally. Imagine the pulley as a peg, like a nail, which is just put inside a wall and the rope is passing over it. The idea is basically to ignore the size of the R. So we take that R is very small compared to L, so that we can ignore what goes over the pulley. So we can say essentially L by 2 is hanging on the left and L by 2 is hanging on the right. Okay. Now the reference is something very interesting. How to choose the reference? So here we can't see the ground actually. So you must choose the reference. We should not change with time or in any sense. So in case of pulley question, the best way to choose the reference is the center of the pulley, like this. So this should be your choice of reference. And because we have ignored the size of the pulley, so it is as good as a point. So we need not to worry about this length. This length is of no use. We can still call Ly to Ly. If I say M is the total mass of the rope, so as per the reference which I have taken, can you calculate the potential energy of this system right now? Can you? Now it seems that it is not a MG. We cannot apply the formula MGH because MGH we apply for the object which are point objects. And what we can see here, the rope is hanging from the reference. So it is not at one particular point. It is actually spread. Okay. So in such case, what we do is we take the concept of center of mass. So for the calculation of potential, you must think of center mass as the point object. So let's take two objects of length L by 2 each separately. The center of mass of the first object will be somewhere here, and the second is also here. So the idea is to calculate the potential energy of center of mass instead of the object. And now for linear object of uniform mass distribution, we take center mass at the center. So that's not a difficult job. Okay. And if you look at this center mass thing, where you can find it? So you'll find exactly at L by 4 on each side. And this is called center mass. Now we write the potential energy for center mass. Okay. So the better way of writing is, let's say, choose something called lambda. Lambda is called the linear mass density. Which is called mass per unit length for uniform mass distribution. So for uniform mass distribution, the lambda is m by L. And now you can think of this as a 2-point objects kept like this. And the height or these 2-point masses are kept somewhere here. You can imagine this way. And these 2-point objects are at a height of what value? What is the height? Below the reference by L by 4.
L by
And what is the mass of each point mass? It is differently m by 2, m by 2. So how to write the potential energy of this system as per the reference? Minus m g h, and because it's a repetition, we can just multiply 2 times. You can see the initial potential energy, because I'm taking this as the initial configuration. turns out to be minus mgl by 4. Okay. Now what we do next? So let's say you pull one of the side. You make a slight pull like this. You pull it downward. If you pull it slightly downward, maybe by a millimeter difference, technically it will start moving because the pulley is smooth frictionless. So once we increase the weight on one side, the gravity will pull on that side and it will start moving that way, as we've done in the case of Newton's laws of motion. And eventually the rope will fall off the pulley. Eventually the rope will fall off the pulley. So find U final at the instant rope leaves the pulley. So I hope you are getting the meaning of it. It means when the entire length is on the one side. Understood? So what is the meaning of the rope leaving the pulley? When all the rope on the left will come virtually on the right, and therefore it will leave the pulley because now there is no rope which can pass over the pulley. Okay. So keeping the same reference, what is the final potential? Tell me, what is the U final? Pardon?
minus mgl by
Correct. So now when the entire rope will come on the one side, the center of mass will be at L by 2. And that is below the reference, we can write minus mg L by 2.
Sir,
Yes.
sir, when the entire roof will come on one side, then the whole length half the center of
Then
mass. Sir, ma'am, okay.
yeah. So now the center of mass will be at half of the length, right? Which is L by 2. And now because this is U final value, so now we are good with the next question, which is generally asked in the examination. What is the speed of the rope at that instant? We need to find the speed actually. So what we do is we apply the conservation of energy. So now this way of writing is very interesting. So now maybe the third question I may ask you that find the speed of the rope at the instant it leaves the pool. So as we know, the only force acting is gravity, and therefore it is conservative force. So energy must be conserved. In fact, the mechanical energy must be conserved, which we'll discuss in a while. And therefore, you can proceed with the formula that K initial plus U initial, which is called the mechanical energy. The sum of these two must be equal to K final plus U final, which is the final mechanical energy. So in the very beginning, the kinetic energy was 0. The potential we calculated, the answer was minus mg L by 4. And finally, we can write the answer as half mv square because I don't know the speed. Let's call it v. And the final we know. That's interesting. You just need to solve this expression, which is mv square, and this will turn out to be mgl by 4. And this will give you under root of gl by 2. Now, if you go back to the notes of Newton's laws of motion, you must have this answer also. and there we solved using the concept of acceleration and the kinematics. Like we got the acceleration as a function of x. So you displace by some x value, and then you find the acceleration, and then you integrate by writing a equals to v d by dx to get the velocity. So that was the
Yes.
very first way of doing it, and now we are doing it with the concept of energy. And this way is particularly much faster and much efficient than the previous way. The only catch here is the concept of central mass. Like normally, the mistake that we see in calculation by the student is that they forget that mgh we write for the point object, where h is the height of the point object. So now in case of objects which are not a point object, which are like somewhat distribution of mass, we call it distributed mass. The mass is spread over the length of the rope. In such case, we use the concept of center mass. And in the very next chapter, when we learn about the center mass, we can write the potential energy for some complex distribution. So right now, we are taking a very simple case of a line, or you can say linear distribution, in which the center mass is essentially at the center of the length, and that is easy to calculate, and so you can do such calculation. Now, this kind of question is very much common in almost all competition. So, if you are talking about the competition, then the potential energy or this particular question is very important. So, let's do
Sir,
some more practice before we go to the next one. Yeah,
sir,
someone is saying something.
sir, in the
Yeah.
previous problem, sir, if two blocks are attached to the pulley, then center of mass will change.
So, when you have a block, then you have to write the potential energy of each block separately. In that case, the rope will be massless mostly, and then you can write. Understood? So if I
Yes,
attach two
yes.
blocks to the two strings, then basically what you have is the 2 point masses. And choosing the datum or the reference at the center of the pulley, you will be able to write the potential energy if you know the height. Okay. Okay. So let's do this new problem. So what we have is a table, and then what we have is a chain, and it's a smooth table. The mass of is m, length is l. So let's say if I pull the chain slightly off the table and release, you're getting a point. If the chain is slightly pulled off the table and released, what will happen is the gravity will do its job. So gravity will keep on pulling it downward. So even if you pull it by, let's say, dx ahead, the gravity will eventually pull it down. So what we are supposed to do? Find velocity, basically speed of chain at the instant it completely leaves the tube. So now again the question is simple. The choice of reference is a common sense. So now you need to think about where you should choose the reference. Now tell me what is the most suitable choice of reference, where we should take.
So like surface of table.
Correct. So the best choice is take the surface of table as a reference. And once you do so, you will be at ease of writing the answer. So tell me the answer. Solve this question, tell me the answer. So what is the initial potential energy? If this is the reference, then what is the
Zero.
initial potential energy? And at the instant of leaving the table, what is the potential energy?
MGL.
Pardon?
MGL
So is it below the reference or above the reference?
minus MGL.
And is it either the position of center mass? Are we writing the potential energy of center mass?
So then minus MGL by
We must look at the point called center mass, not the chain. The chain is spread from 0 to L. So when the chain will be in the vertical position, leaving the table completely, the center mass of the chain should be taken into consideration while writing the potential energy. And where it is L by 2 below the table, right? The reference. So this must be equals to minus mgl by 2. I hope this part is clear to all of you. So now the center mass is here and it must be L by 2 below. So when it comes to the linear object, as I said, you must write the potential energy of
under
center
root
mass,
GL.
not small. Yeah, so now we can write the formula energy consumption K initial U initial. I write it in step 0, 0,
Plus 0.
half mv square. So the V turns out to 1 to. So I hope you can say desirable in various competitive exams. It's not a difficult job. Now the once you read the next chapter called center mass, then this can be made very complex. So the formula for potential energy is not mgh. So the better way of writing this, the potential energy we all write as mgyc, and ycm is the y coordinate of center mass of the body with respect to some reference. With respect to datum or what we call reference. So in writing the potential energy, that the concept of datum is important. So you must choose the datum, and you also should stick to the data while doing the problem. So you should not change the data elsewhere. Like you're doing one, you're writing the initial with one datum and final with another datum. That will be the wrong answer. So the rule is the initial and the final must be written with respect to same reference. You should not change the reference while doing such calculation. Of course, for various other problems, you can choose a different reference or datum, but at least for one problem, you must stick to one datum. Or not one problem, you can say for one particular comparison of initial and final. So initial and final, we must write with respect to the same reference. If you go with the other sub part of the problem, in which again we need such calculation, you may change your reference. That's not an issue. Okay. Now this was the work done by gravitational force. So now once we understand the potential, now we are good to go with a new concept called conservative force. So the next topic will be, okay, just remind me at the end of the chapter, I need to give you some other miscellaneous problem that is called work done by friction and the chain problem. So how to calculate the work done by friction when the chain is falling off the table and the table is rough now. So that one particular question I wanted to take actually, which I just forgot in the last lecture. And because we are doing the potential, I want to proceed with the potential. But once we finish it, I'll give you some of the examples. Okay, so the next concept will go with the next concept that's called the uh, meaning of can say conservative and non-conservative forces. So now, before I define this, let's discuss some of the literature, the word meaning of in normal sense, in normal English. So when you say conservative, what do you mean? So if we talk about the belief system, people who are conservative, they want to stick to their old tradition, roots, and they don't want to change with time. So they are like non-progressive in nature. So they believe what they believe is true, and they don't want to make any changes to it. I mean, the belief system is very conservative. We call it. So in other system, we call it orthodox. People who don't change. So the conservative means to conserve something, to preserve your tradition, rules. That's also called conservative. And that's exactly what we actually also define in physics. So when I say a force is conservative, it means its nature or its characteristic is somewhat intact. It's not changing. So let's talk about the gravitation for the example. So let's talk about the our solar system. And in solar system, we see that no matter where the planets are in their orbit at different points of the year, the force of gravity always acts towards the sun. So the attractive force acting on all planets is acting towards the sun. And no matter what is the position, it is always directed there. So we say it's like a conservative force because the characteristic is to act towards the sun center, the center of sun. And that characteristic is not changing with time. So no matter where the planets are, the directional force remains always towards or always remains directed towards the center of sun. Such force we call central force, as I have said some time back in some lecture. And the property of central force is that it is always acting towards some center. So in this particular case, the center is the center of mass of sun, and it is always acting towards that center, and therefore we call such force as conservative because this is trying to preserve the nature, the way it is acting. So if we have a force which is permanently constant, so we can say it's conservative because something which is permanently constant is not changing at all. So it's conservative. Now let's talk about the friction force. If you go right, it will act left, but if you go left, it will act right. Let's talk about the kinetic friction. So now definitely the kinetic motion is changing with situation. It is not trying to maintain the way or its characteristic. So we say that it is non-conservative. It is kind of progressive. So the forces which essentially maintain their some characteristic we call conservative, and if they change their characteristic, if they behave as per the situation, in most of the cases, we call it non-conservative. So for example, the air drag or any frictional forces. So if you ride your bicycle, let's say you're riding your bicycle, if you're going towards east, the drag of the air will act towards west. And the moment you turn your bicycle, the drag will change. In fact, the drag will always act opposite to your instantaneous direction. So you may say that the drag force is something which is very much, you know, adjustable in nature. So the way you change your motion, it will also change its way of action. So they don't try to maintain the status quo. I mean, they don't try to maintain their characteristic in one particular way. They keep on adjusting and keep on changing. So in a sense, they are non-conservative. They don't want to conserve anything. They want to change. They want to keep on changing. So we call it non-conservative. They're not something trying to maintain their property or characteristic. And because of this particular reason, it is almost impossible to actually have a absolute definition of conservative and non-conservative forces, because at a microscopic level, everything is conservative. So nothing changed at microscopic level. The word conservative and non-conservative is only used macroscopically, that is on a large scale. So let's say if you give a glass of water to a small kid and tell him to carry it from one room to another room, there is a very high chance that the water will be spilled out or splashed out of the glass while he's taking it from one room to the other. So in a sense, that water may not be used or consumed and used for the consumption, because it is lying on the floor and probably will not go and uh, like take a sponge and absorb and put into the glass of water in glass. So for you, it's kind of lost in it. But essentially, the water is not lost; it is still lying on the floor. So if you take into consideration of the entirety of the universe, nothing is lost because everything is somewhere. But for the purpose of usage, we can say that a certain amount of water is lost. And that is exactly the behavior of non-conservative force. So when some energy is lost and not in a like a mode or the form which can be used again, we call it non-conservative. uh, Work done of the non-conservative force results into some loss of energy which cannot be retrieved. It converts energy into a form which cannot be taken back. Conservative forces never convert energy into a form which cannot be taken back. Rather, their property is to restore the energy. So when they do the work, let's say if a conservative force is doing some positive work, they decrease the potential because they use their own conserved energy. And when the conservative force will do the positive work, it will store the energy. It will keep, it will extract some extra energy from somewhere and it will store somewhere. It will never waste it. So the basic definition or the basic difference that we need to realize for this particular chapter is that the work done by conservative force, if positive, it means it will always result into increase of energy to the system. Conservative force never wastes the energy, and that's why the concept of potential is only meaningful in case of conservative force because they keep energy, so they conserve in a sense, and that's why we say that potential energy is a definition which is only meant for conservative forces. We don't use it do not define potential energy at all for non-conservative force because they waste it, they throw somewhere. So the chance of getting it back is very rare. We may devise some mechanism to actually extract such energy, but we cannot, in fact, convert this 100%. So we always have some fraction by which you can retrieve. And this idea is very powerful idea called retrieving the energy from the such system, and this idea is called the thermodynamics. So thermodynamics is a way to extract energy from the microscopic losses, which is a general loss, but we extract the energy from the loss also. So I'll tell you how we can do this. So now conservative and non-conservative force having no clear demarcation actually. At one level, something is non-conservative, but another level it is conservative. So for example, if you rub two surface, it will produce heat energy. Now the heat energy is nothing but the energy of the gaseous molecule. And the energy of the gaseous molecule is nothing but the kinetic energy of those gaseous molecule, like their motion, their kinetic energy. So if somehow we can take into consideration such energy, which is the energy of the every individual gas molecule, then nothing is lost because energy is there. But as I said, that energy is difficult to retrieve in a sense we can understand. So I cannot go and ask the O2 molecule in the atmosphere give back my energy. I mean, it's like a ridiculous question. So taking energy back from the gas molecule is not an easy job, and there is no way by which you can retrieve 100%. And that is why we put into the category of loss. So we don't say, we say that because I am talking about a block. Let's say if I have a block and if I throw on a rough surface, my block will stop. The reason is all of the energy of the block, which is the kinetic energy, is actually dissipated by the friction as a heat energy. Now the heat energy is also energy which is available to the gas molecule, but we cannot go back and request gas molecule give my energy, and I can reverse the process of block coming back to its origin. So that's not possible actually. So in a sense, it is lost. We call the, in a macroscopic sense, it is lost, but at a microscopic sense, it is still somewhere. So that is why I said that the microscopic world never talks about the non-conservative. The word conservative and non-conservative is only at macro level, the bigger level. The big picture is lost. And why it is lost? Because the system that we are talking about is losing that energy. Okay. So we are not taking the system as the entire universe. If I take the entire universe as system, nothing is lost in a way. So that's exactly is the idea behind the conservative and non-conservative force. Now, as a student, what you need to know? So what you need to know is that all field forces are conservative. All elastic forces are conservative. So when we have an object with 100% elasticity, which means something which can recover their deformation 100%, which is like a spring. You deform it, but once you remove the force, it will go back to its original length. So that's called 100% recovery. And we say it is perfectly elastic system. So any system having the restoring ability up to 100% will define a conservative system, or the force by such system we call conservative. So a spring force, or more general the elastic forces, under the range of perfectly elastic condition, when they can recover absolutely everything, within that range we call them conservative. But if you go beyond that range where the recovery is not 100%, some deformations are permanent, we do not call it potential. I mean, we do not define the potential for such system. So now coming back to the definition, what are the properties of conservative force we need to discuss? Now the definition says that it will keep the property intact, which means if you choose a path which begins and ends at the same point, so let's say you make a journey and you go and you come back to the same point. This is the beginning and end. We call such journey as a round trip journey. Now the property of the conservative force is that they maintain their characteristics. So whether you go away from the beginning or when you come towards the beginning, the way they act is always same. And that is why while going away, if it is doing positive work, so coming closer to it will always have a negative work and vice versa. And therefore, if you come back to the same point where you began, no matter which path you chose, the conservative force will always do the zero work then, because it will do exactly the positive and negative one. Because if I define going away as negative, then coming towards is positive. If I define going away as negative, then coming towards is sorry. If I define going away as positive, coming towards is negative. So the idea is that no matter which path you choose, if you go back to the same point where you began, the total work done by the conservative force is bound to be zero. Now, I'm not saying the other way. If some random force is doing zero work in the some particular closed path called the round trip journey, that is not the case of or the criteria to determine the conservative force. I'm saying that if a force is known to be conservative, then it will have this property. If some force will exhibit such property and will become conservative, is not true. So let's say if you're a doctor, then you will wear some apron, let's say white apron and the oscilloscope and so on. The other way around is not true. Like if someone is wearing that, will not make them doctor. So you have some inherent characteristic to become doctor. You will have some MBBS qualification, you will have a degree and so on. You will have some examination. So similarly, if a force is doing a work then zero in a round trip, will not make them conservative. Rather, we know in advance that the forces which are conservative will have this property. So there is no absolute distinction of which is conservative, which is not conservative. But for the syllabus that we have, we know in advance that these are conservative and these are non-conservative. So let's write the properties, and you need not to worry much because we have very few conservative forces that we deal with. So we have gravity, we have electrostatic force, we have spring force. These three bunch of force, I mean, these three forces are essentially conservative force that we deal with. Any other force we don't call conservative. So conservative is meant for the forces which creates field. So we have gravitational field, so it's conservative. We have electrostatic field, so it's conservative. And we have also elastic potential energy because that is some sort of some field, because that's difficult to define right now. But I will define there's something called uh, energy density, elastic energy density, which is also some sort of field only. And the elastic potential energy we define because of the nature of a recovery of 100%. Like you recover everything. So if a deformation in the body is recoverable at up to the extent of 100%, then we can define such internal forces as conservative forces. So spring force is conservative force. That you have, that is something which is not very intuitive, but it is something which you need to remember. Okay. So now we are done with the theory. So we can just define something. We'll end up adding some properties. So what is conservative force? So actually, what is conservative force is difficult to define. What we define is what are the properties of conservative force is the better way of actually saying about it. So we can also say that a force is said to be conservative if its work done is zero in a round trip journey, no matter which close path we choose. So if you choose one particular path and perform zero work, that is called one exceptional case. But if I choose any random path and you end up giving the same answer, let's say if I make infinite trials and in every trial we see that the answer is zero, then am forced to convince myself that this force is conservative. So what you can write is a force is said to be if its work done does not depends on any path taken. So if your work has nothing to do with the path, if it has only to do with the beginning and the end, then definitely you are in the category of conservative force. Not no one knows about this in advance. Of course, you have to do the practice and complete. So force is said to be conservative if its work done does not depend on any path taken. Rather, it depends upon the beginning and end of the job. So now we have a very special kind of a name for this. So work done by conservative force is point function. So mathematically, it depends on the beginning and the end point of the journey. It is not a path function. So it does not depend on the path which you have taken. So if you remember the maybe last lecture, yes, or no, last lecture. In the last lecture, we did something for work done on a path A, B, C, D, and we saw that by choosing different path, we were getting different answers. So work depends on path, and because it depends on path, so definitely there was an example of non-conservative force because you have different answer for different path. But if the force is conservative, then no matter which path you choose, you will end up getting the same answer. That's why we say that work done by conservative force is a point function. It's not a path function. And that is why the work done by conservative force is only meaningful when you change the point. So if you are at the same point in the very beginning and at the end of the journey, then we cannot distinguish between your like journey. So for us, there is no work. So we say that in a round trip journey, there is no work. That's why we say work done by conservative force in a round trip journey is always zero. Why we are saying this? Because the round trip refers to the case when you begin and end at the same point. So apparently there is no difference because your location has not changed. So now we can add something called properties of. So the first property is what? Work done by conservative force in a round trip journey is always zero. Now, this definition is a consequence of the above definition that work done by conservative force does not depend on the path, it depends on the beginning and the end point. If the beginning and end points are same, then we say there is no work done. Okay. So, second property we can call it if you see a question in which a force is behaving as a central force. So, for every central force, the work is always the work done is always conservative. It means a central force will have behave as if the conservative force, and if the beginning and ends are against him, there is no work. So all central forces are conservative. So a force which acts toward the center, you can treat as conservative. Let's say you take a rope and if you put a stone and a wheel in a circle. So basically the tension is acting towards the center all the time. So for that particular motion, if you consider tension as conservative, that's okay. And because in that case, if you talk about the round trip journey, or even for in fact the work done by tension is going to be zero for any path. But for round trip journey, it is definitely zero, no matter how you move, because the force of tension is acting toward the center. So it's like central force. So every central force will be behaving as a conservative force. So what are the examples of central force? So you can say gravitational force are central force. Electrostatic force of the charged particles are against central force. So they act either towards center, they act away from the center also. So it is having some peculiar characteristic which is intact, so we call it central force. So in fact, all forces acting between charged particles are always conservative if the force is electrostatic in nature. Okay. So when two charge or two mass will interact, the force is bound to be conservative without any confusion. It should not have any confusion or any dilemma. So just remember that. So what is the third property? The third property says that the potential energy concept is only meant for conservative forces. Like we do not define potential energy for any force. No, that's not possible. So the conserving properties with conservative forces and the ability to conserve something is for potential. So the potential energy is only meant for conservative forces. So potential energy is only defined for conservative forces. So if we have a gravitational force, electrostatic force, or a spring force, we can say potential energy we can define for such forces. We do not define potential energy for air drag, friction, viscous. No, they waste the energy, they dissipate the energy. They are energy dissipators. So they cannot conserve energy. For example, if we talk about the resistance in a circuit, so resistance is the energy dissipator, and therefore we cannot define potential energy of a resistor. It will always waste or dissipate the energy. But if we talk about the capacitor, if we talk about the inductor, for them we define potential energy. So we have electrostatic potential energy or energy stored in capacitor. We have energy stored in inductor, and all are potential energy. So they are energy storer. Okay, they don't dissipate. So in an electrical circuit, when you will study in class 12, you will come to know that we also apply the energy conservation in a circuit where there is no resistor. So let's say if we have an inductor attached to a capacitor and there is nothing else, and if I give some charge to the capacitor, giving charge to capacitor is as good as giving energy to the capacitor, the potential energy, and that potential energy will oscillate from the capacitor to inductor and vice versa. So that energy itself is the potential energy which oscillates between the I mean, you can say two circuit elements called capacitor and inductor. And we also have a name for this phenomena called LC oscillation. We call it LC oscillation, which is essentially the way to create the resonating circuits. Okay, which is essential part of tuning the different channels. So in the earlier when we had a radio. So radio had a circuit called capacitor and inductor, and when you turn the radio on and you make a knob turn, what you do is called tuning. A tuning is like setting the L and C value, which can create a frequency similar to the frequency of the given channel. And whenever there is a match of that LC frequency with the channel, it will create the resonance, and therefore you can listen to that particular channel. Now the same thing is done nowadays digitally. So we have a digital circuits mostly, and the tuning is done automatically. So what they do is the same thing. Eventually, some sort of resonance is created, which catches that particular frequency, because the space around the radio is filled with infinite frequencies. So which frequency you want to listen to? So there's something called resonance of tuning actually. So again, the energy, the LC oscillation is very important. So if the LC oscillation frequency matches with the frequency of the electromagnetic wave, then it will catch that wave, and that's how we tune our devices. That's how we watch our favorite TV channels. These all are based on the some sort of LC oscillation. Now, nowadays this is a very complex method. So they have a different way to interpret and actually make it work. So potential energy is only defined for conservative force. That's true. The other definition we can say is like all field forces are conservative. So all forces, I mean, which creates the field like gravitational, electric, electrostatic, and magnetic, these are conservative by their nature. So those who create the field are conservative. There may be some exception that we'll talk about in a topic like magnetism. I'll tell about something called non-conservative electric field also. So we do have something called non-conservative. So electric field is generally developed due to charge. Generally means in 99.99999% case, it is the charge which creates the field. But there is one particular scenario in which the electric field is created without charge. It is like every person is born, but there's some avatar also. Now that is of course a hypothetical case. So in physics, all electric field is due to charge, but there is one particular way in which we can also create the electric field called electromagnetic induction. So by changing the magnetic field with time, we can also create electric field which is not by charge, and that is not a regular process of doing it. So we call it non-conservative field. So don't worry about those complex example, but for this particular chapter, you can remember that all field forces are conservative. So conservative forces are always there. Now, the bond energy, which you call bond energy in case of molecules, let's say two H atoms combine together to form H2 molecule. The bond energy is nothing but the potential energy of interaction of two atoms. And when it is, I mean, when the bonds are created, so when the attractive force and the repulsive force balances out each other, then the separation at which these forces are balanced is called bond length. Okay. And every system will lose, let's say, two H atom when they combine, they form H2 molecule. In the process, they release energy, because a creation of molecule is a stability. I mean, you go towards the greater stability. So when you create a molecule, you go from high energy configuration to low energy configuration. So what nature creates is always in towards the lower energy configuration. So when you create a H2 molecule out of two H atoms, then definitely the H2 molecule will have an energy calculation which is less than the sum of energy of the two H atoms. Because the very purpose of creation of molecule or any stable configuration is to minimize energy. So the potential energy in such process will decrease. Okay. So we'll also see something called the Lennard-Jones potential very soon. So all field forces are conservative. That is what you need to remember in a very simple. So now we are in a position to define some relationship between conservative force and potential energy, because this is only defined for conservative force, so there must be some relation. Now, as an example, what you should remember, gravitational, I'm just putting it explicitly for your reference. Gravitational force, electrostatic force, I think I can say for example only. Electrostatic force, spring force are conservative. So for you, for your this chapter, always remember that the first and the last is your concern. Anything other than the first and the last, like gravitational and spring, if you don't see these two names, you call it non-conservative. Like friction, tension, normal, you just say it non-conservative, don't say it. So gravitational force, electrostatic force, spring force are conservative force. Okay. So then what we can say or talk about the non-conservative force? I mean, because it's just other the complement of what we just learned. So you can say non-conservative force. So if you talk about the non-conservative force, then we can say that the work will depend on the path. Now it's other way around. So work done by non-conservative force always depends on path taken. That is work done by non-conservative force is path function. So you need to know the path, then only you can define the work. Without path, you cannot. Without the knowledge of path, you cannot define the work done by non-conservative force. Okay. So what it does, so if non-conservative force will do the work, it will either dissipate the energy or will do nothing. But they cannot increase the energy of system. So they can either dissipate or do nothing. So either no work or negative work, but not a positive work on a system. So that we have discussed in already in the some other case. So work done by non-conservative force can be zero. It's not like it cannot be zero, but it can be negative also. And if it is negative, it means it is going to dissipate the energy. So we say that work done by non-conservative force on a system always results into dissipation of energy. Okay, it could be doing nothing also. Let's say if we talk about the static friction, then static friction we have discussed that it will never dissipate the energy. It can do work, but it will never do work on a system. It will do always zero work on a system. So if we have internal constant force, it will do zero work. If the force is not constant and it is internal like kinetic friction, it will result into dissipation of energy. So when we talk about the non-conductive force, it is not necessary that it will always dissipate the energy. It can. The idea is it is having the ability to dissipate in cases, in a situation. So that's why we say the work done by non-conductive force either may be zero or negative. It is generally not positive on system. Okay. So for system, it will do either nothing or will do some negative work. Okay, so anyway, we'll write the properties. So you can say for a round trip journey, work done by non-conjunctive force may be zero or negative. Okay, it will not never be possible to vary. So work done by this in a round trip journey, it will be like zero or negative. What is the second case? So you can say negative zero, it may be positive. Let me see some example if it is possible. Normal. Yeah. The second is generally, I mean not always. That's why I put a word generally. Generally, work done by non-conservative force results in energy dissipation. And this dissipation occurs in form of heat. Okay. So whenever there is an energy dissipation, we say work done by non-conservative force is equals to delta H, the heat dissipation. So we can compare these two values. The third point connect is we cannot define potential energy for non-conservative force. So potential energy is not defined at all. And what we can write next? So you can just put a name some examples. All drag oblique frictional oblique viscous forces are non-conductive force. Now drag we use for the gases, friction we use for the solids, and viscous we use for the liquids. So when you face the frictional force by liquid, we call it viscous. When you face the friction by gas, we call it drag. And then we have a solid surface we call frictional force. That's how we name it. So we call air drag kinetic friction and the viscous force. All drag, friction, and viscous forces are non-kinetic forces. This is something what you need to remember. Okay. And okay, that's it. That is sufficient as a concept. We are supposed to only know this much.
Sir, I want to know the last point. So,
All are same thing. Drag, friction, viscous are just a name given to different medium. So there's nothing like big deal about these names. So you can call it friction everywhere, but we have a nice nomenclature for
done.
each. Okay, so now we are good to go with the next concept called relation between conservative force and delta E. Now, this is the definition which you are supposed to remember, and it is a must for everyone. So in competition, you may expect question from here, especially in NEET, it's very common. Every year, you can expect at least one question from here. So we say that work done by conservative force is equals to loss in potential, and that's meaningful. Why? Because when I say conservative force, you can think of gravity, spring, or electrostatics. Now, this chapter is not about electrostatics, so you are not going to face any work by electrostatic forces. So your work will be limited to spring and gravity. And if spring is absent, then only gravity. If gravity is not absent, is not possible. So gravity is always there. So now work done by conservative force means when the system will do the work, it will do at the expense of its own loss of energy. So it will use the saved energy in the past, so the potential will decrease. So when a conservative force is doing positive work, it is consuming its own energy. If it is doing negative work, it is consuming someone else's energy. It is taking from somebody else and storing it to us. So work done by conservative force is always equals to minus delta. This is the most important relation which you need to remember. Okay. And now we know, let's say we have a one dimensional case. Let's say we have a block. Let's say this block is under the influence of some conservative force. So we call it FCF. So I'm just naming it conservative force. Some conservative force is acting here. And now this block is taken from here to here. So let's assume this is the elemental displacement. So let's say call it x position. Let's call x plus dx. Because no matter whether the force is variable or constant, no matter what, in the small displacement, it is going to be constant. So what is the work done by conservative force? What you can say? What is the work done? dWCF is how much? So we can let's call it F only. Right? We can say FDX, right?
Yes.
So if the potential of this particular location we call it U, and if the potential of this location we call it U plus dU. So we know what is the change in potential energy from here to here while going from here. So this must be equal to how much? Minus delta E, which is like final minus initial. So minus final minus initial. So we can see that the f dx turns out to be minus du. And now this gives the definition that what is force? It is the first derivative of potential energy with minus sign. So in one dimension case, in 1D problems, if you see a potential gradient, which means if you go in along x-axis and if you see potential is changing, it means the force must be present in that direction. Because unless there is no there is no conservative force, we cannot have work, and we cannot have work means we cannot change the potential. So the other way of saying is that if I move in certain direction and if I say the change of potential, then I can infer that some conservative force must be present in that particular direction. Understand?
Yes.
So imagine if you are standing on a long pillar, you're top of the pillar. So let's say if I blindfold you and make infinite rotation near the edge of the pillar, and if I tell you walk one step ahead, so you never know whether you will fall off the pillar or you may remain on the pillar. Okay. So let's create a boundary, something like this. And a man is blindfolded and now he's standing here. So you're supposed to make one step. Now you can make one step in any random direction. So what are the chances it will fall? So the guy can make one, 360 direction. You can move in any direction. So half will save you and half will let you fall. The chance will fall is 50% in this case. So when you make one step in this direction, you will save, and this direction over and out. So it means if there is a difference of potential, there some force must be acting there. So when you move in a direction and you see there is no change of potential, which means one thing, that no further work has been done by the conservative force, and so the saving is maintained. That's all you can think of. So when potential energy of a system is changing, it means some work is being done, because we know that to do some work we need energy. So when energy is constant, it means nothing is done. So if you walk in a space where the potential energy is constant everywhere, you can always say that there is no work done by conservative force in that space. In fact, that is also a way of saying that no force is present in that space. Why? Because you can move freely without the hindrance of force, and that's why the potential will never change. Because potential to change, you need to do work, and work is not happening because there is no force at all. So if you move in a space, let's say we have taken the one dimensional example. If you move in one particular direction and if you see there is no change of potential, you can say, oh, there is no force acting in that direction. So now how we can extend this to the three dimension? So we can extend this definition to three dimension. Although even if you remember the formula, that's good enough, but I'll try to give you some intuition which may be helpful. I really don't know. So let's say this is y axis, x axis, this is z axis. I choose a random point P here. And then I redraw the x and y there in coordinate coordinates. So this is the point P itself is at a point called X, Y. So if this is the point in a space, let's call the potential of this point as V. Okay. So now we have no idea that how potential will change, but we can expect something like this. So let's say when you move along x-axis from that point P, so the new potential which you may find may be U plus some new value. So let's say the potential is changing at a rate called del U by del X. This is the rate of change of potential when you move along x-axis. It means the gradient along the x-axis. And this del is called partial derivative, which means I want to understand at what rate potential is changing due to the variation in x only. So I'm not taking y and z as variables. So I'm taking one variable at a time and assuming other variable as constant. So what if I move along x dash? So let's say the potential is varying along x dash by a relation del u by del x. And if I walk by length dx, this is the net change. Okay. Similarly, if you walk from point P along y dash here, so the new potential there will be u plus the rate of variation of potential along y into the length you have walked further. So I'm saying dy. And similarly, if you walk along z axis, the potential may change by this value del u by del z. This is the rate at which potential is changing, and the distance which you have traveled dz. I'm taking elementary displacements dx, dy, dz. And imagine that at this particular point we have force acting fx here, fy here, fz here. So let's write the work done by each separately. So what is the work done by fx? So we can say fx dx. And this must equal to what? Minus delta E. Minus delta E means what? Final final minus initial. So what it turns out to be? Fx dx equals to minus u we consider. We get a minus del u by del x into dx. Now we can cancel out dx because it's same on both sides. We can say the fx is equals to minus partial derivative of u with respect to x. No, I have proved for one. I can just write similarly. The fy you can write as minus del u by and fz. Now u is a potential which depends on all three values x, y, z. So I'm saying u depends on three variables. So when you say del u by del x, what does it mean? Differentiate the function assuming only x as variable and treat y and z as constant. Okay, that's the meaning. So the potential, if changing in one particular direction, it means the component of force is present in the direction. I'm saying component, not the force. So now by evaluating three component x, y, and z in three mutually perpendicular directions, we can claim the force value because we know that every force in three dimensions must have, I mean, at a max it will have three mutually perpendicular components. So if you know all three components, you can actually recreate the force. So now we know the component. So how to write the force? What is F at that point P? So at point P, if I want to know the force value, you can see the force is equal to how much? The X component I cap. So we can write like this. So what we are doing here is that you are at P. So think this: you are at P, and you try to move one step ahead to check if the potential is changing or not. So whether or not the potential is changing. If you see there is a change, you will say that okay, there is some component, because potential can only change when there is a work, and work can only be done if there is a force. So change of potential is signifying that some component of force is present in the direction. And by the suitable choice of the three coordinates x, y, and z, we make sure that we can exactly determine three components. And once I know three components, I can recreate the force which is actually present at that particular location, which I don't know initially. And now I have the force. So what we can add F equals minus, I'm taking minus 1 plus del u by del x I cap. It is called either del or do. So you can say douj do. So different professor will pronounce differently. But del is a very famous. And now this we can rewrite as del by del x I cap del by del y. And you can see I have put u basically outside. I don't have slope actually. Because we are applying this. This is called operator. So in math we call it operator. It operates on value u. So this entire thing you apply on you. Let's say when you say dy by dx, what is the operator? D by dx is the operator, and you apply on what? Y. So y is the value or function on which you operate this. So this is called operator. And those who are not aware of operator, I think I have explained this operator thing in the
Yes,
basic. Yeah. So now this is a big operator. Now you have seen maybe singular operator, but this is something called you can say a variety of operator put together. So there are three operators doing their work together, and because it's a summation of del by del x, del by del y, del by del z, so we call it a del operator. There is a name for this, and there's a symbol for this also in physics and mathematics. It is inverted triangle with arrow. So we call it del operator. So we write F equals to minus del u. So what is del? Just a fancy symbol for writing this complex expression. Because at advanced level, calculation becomes very complex. So we need to have some more, you can say, notations which are very crisp
sir, that it
and
means that we have to put the value of u in there.
yeah,
That
I
del.
mean, correct. So basically, del is nothing but this entire operator thing. So del by del x, I cap. So this is like alternate substitute for writing this big thing. So either write three terms this, or you can just write del. That's a nice way of writing. So it gives it a mathematical abbreviation. You know, this is a simpler way of writing. So we say that the force, now force is that means the net vector force, not the component. The force is nothing but the negative of del. So what is del? Del is called del operator. This is also called del operator. This is also called nabla operator. But the best name is called gradient. So we call it gradient. Gradient is a fancy name for slope. And slope in that one dimension we call it dy by dx. Because in one dimension we have only one variable x and y is the value which depends on x. So we call it dy dx. But del is a general way of writing slope in any dimension. Basically, you're learning 3 dimension up, but it can go up to 5 dimension, 10 dimension, or infinite dimension. But don't worry about this. Does it
So
mean?
what is the
Let's say
second one?
what is the gradient?
Second one.
Nabla. So this is nabla. 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 Just named for the same operator. So you call it nabla operator, del operator. The best way is called gradient, which is very meaningful. Gradient is like the slope in general scenario. For example, let's say you think of a dome. You can think of dome. So if it is really big dome, I mean, someone might have experienced that you can walk along this path easily. You can walk horizontally. But if you try to walk this way, it's very dangerous because slope will keep on increasing. But if you walk like this, slope is maintained. So near the top of the dome, you can walk. But as you go down, then its slope will grow because the slant will grow. You can see. Now, if you walk this way, your slope will not change because you are essentially at the same level. So everywhere, if you draw a slope, it's same. So now slope is changing. If you talk about the direction of change of slope, it is downward. But if you move this way, slope is not changing. Difficult to realize. So in three-dimensional world, we may get some direction in which there is no change of slope. Didn't get. Yeah. So imagine we have an inclined plane. So you can see this slope is changing. In which direction it is changing at a maximum rate. If I walk like this, so if I walk like this, if I walk like this, let's say there are 3 ways in which I can move. There are 3 paths. In which case it is most challenging to move because slope is changing. The rate of change of slope is maximum. In which case? In which direction? A, B, or C? In which direction the slope is changing at maximum rate?
B.
It is B, of course. B for mountain. A B is changing, but not as steeper as B. So B is called the line of maximum descent. What do you call B? Line of maximum descent. 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 In C direction, if you walk, nothing is changing. Okay. So C is having 0 gradient. You can see. A will have somewhat gradient. B will have the maximum gradient. So now, so far, you have been walking in one direction. So we had dy by dx. So what if you can walk in a variety of directions? So let's say if you're at the top of a mountain, and there is some and now this is the steepest descent. So you can come down from the top to the bottom, and which one is the most dangerous path to choose? So I have marked with the blue line, somewhat light blue, turquoise. You can see. So now this path is the called path of greatest descent. It's very steepest path. So in the real world scenario, we don't have one particular way of moving. We have infinite ways of moving, and therefore every direction will offer you different gradient. That's the idea. So in one dimension, if we have, let's say, if you go to like some water park and if you see some rides, it is one dimension because you can only move this way. There is a small part you can walk like this. This is one dimension. So we call it slope here. We don't say gradient. We call it slope. But what if we have a freedom to move in random direction? So if we have a random slope in random direction with a very complex gradient, maybe different gradient. Some is very steep or something. So now if you fall from here, then depending on which direction you fall, you will have different acceleration or the way of moving down. So we call it gradient. So gradient is actually, I mean, defining the different direction and different slope value. The steepness, you can say, the steepness will change. So del is the operator which defines the steepness in three different directions, which are called x, y, and z. Okay, and you want to understand that which direction is most steepest, and if one particular direction is not at all steeper, if it is flat, then the gradient must be zero, which is the reflection that in that particular direction there is no slope. That's that. I hope this is clear to all of. So
Yes, sir.
do you realize what is gradient? It's a way of asking that what is the slope in three separate directions, and we check each direction, and we add them using the I, j cap, I, j, and k cap to understand the net force. So let's do some problem to understand this. So what we can say. So let's say potential energy is defined as x, y, z. Very simple. So it depends on three coordinates, and it is proportional. In fact, we can say equals to the uh, product of three coordinates at that particular location. So question is find force at 1 comma minus 2 comma 3. So find the force at this particular location. This is some random coordinate which I am asking. So what is the force present there? So now we go with each component because it's difficult to say the force directly. So I need to go with component. So I'll just do the I will just differentiate with x and minus n. So because I'm differentiating with x, that is like a number, like 5, 10, something. So it's constant. We can take it out and then we differentiate only x. And now we know how to differentiate this. Just like d by dx of x, which is 1. So the answer is minus y. So this is pretty easy example. You can say fy is minus xz, right? And fz is minus xy, correct? So the force value is how much? It's a minus yz I cap and minus xz j cap and xy k cap. Now you could have substituted the value of coordinate in the very beginning, but nevertheless we can put it here also. What is y here? Minus 2, z3 minus 6, xz 3. What is xy? Right. So now I can put minus an inside. So 6i minus 3j plus. So this is the force acting at that location. You can see there is a 6 Newton acting along x-axis. Minus 3 means 3 Newton acting along minus y-axis, and 2 Newton acting along z-axis. That's the meaning. If anyone having any doubt, you can ask. So is this clear, guys? No. Yes. Answer. Is this clear?
Yes.
Yes.
So can you do this example for me? Maybe I'm giving you maybe x square y is z plus y square z square x square. Can you find force vector at minus one one? Do this question. So now here we have three terms. So when
Sir, it
you
is 4 I cap minus 3 J cap and
Mhm.
uh, sir, I am calculating the Z term. So one, sir,
Okay,
1 minute, sir. So
no.
adding.
So the first answer is 2x, y, z, and one. Okay, so you can do one minus one and this minus two. X z minus s. Yeah, four is correct. And if you do the fy, it will be minus of y, x square z, and this is 2y z square.
Sir, minus 2 K cap.
It's x square y, which is 1, which is 2, minus is correct. The z is minus of x square y and 2y square z and x square, which is x square y is 1, 2. Yes, so answer is 4 I cap minus 3 j cap plus minus 4 I cap, 4 k cap.
Sir, I got minus 2 K cap.
X square y is how much? 1. 2 times y
Yes,
square z is 2. Okay.
yes.
And x square is 1. So
हाँ
1 to 1 is 4. So I'm getting minus 2.
हाँ सर हाँ.
Okay, so now these kind of questions are very common in like for us. Now for you, it's a neat answer. You will ask question like this, very common. So they do have questions like this. Every year, one question you can expect from this particular differentiation part, which is easy and scoring. You can always score from here. All right. So because we can relate potential with force, the other way is also possible. If given a force, can we find the potential formula? So how to go about it? So the way of going this is like so, uh, let me give you some intuition about it. So let's say this is the xy plane and you're going on this random path. This is the path in which you're traveling. And at some instant you are somewhere here. And this is how the force is acting. If I draw a tangent at that particular point, if I draw a tangent somewhere, if I call this angle as theta, because this is not x and y, this is called dl, or ds. That's called ds. So we know that the force along this direction is the work done will be how much? If you go from there to the work done by force. So the work done by the force will be F cos theta into ds. Okay, and we know that work done is equals to minus delta. That's the definition. That's a because we are saying this is a conservative force. I'm demonstrating in two dimensions. You can extend to any dimension. So the work done by the force is F cos theta into ds, which is equals to minus du, because the way, the direction in which you move, the potential will change. And therefore, this is F dot ds. F dot ds equals to minus. So therefore, you can say du equals to minus F dot ds. And now you integrate. So what you can write is delta u is minus, and F dot ds you can write as a sum of three components. You can say fx dx, because you can write as fxi, fyj, fxj, and ds you can write as dxi, dyj. But we can extend to three dimensions. So I'm just doing it for three dimensions. Fx dx plus fy dy, or less for two dimensions. You can write like this. which you can extend for 3 dimensions. Because right now here ds we can write as if I say this is ds, this is dx, this is dy. So ds as a vector we can also write as dx I cap and dy j cap. And f as a vector we can write in 2 dimension as fx I cap and fy. So when you take the f dot ds, you're bound to get the fx dx plus fy. There's no I in here because it's dot product. And now you can integrate. So you can actually extend this definition to 3 dimensions. So for 3 dimension or in general, that we can say the delta is minus. Or you can write it each term separately because that's property of integration. So that we can do. So now there is a very famous question on this. Interesting. We must do this question. In fact. So what is the question? The question is.
So can we show the previous page?
Okay, I put the heading relation between blue and the reverse relation. So we know how to find the force from the potential function. So how to find the potential function from the force? That's the question. That's what we are trying to evaluate. Okay. Okay. So next we can say is an example. So let's say a force is written as y I cap plus x j cap. That's a very famous. So if potential at OO, that is origin 0, 0 is 10 joule, find U at in general point x1. What is U x1? So let me do this quickly. So delta U we have the definition, which is minus integration fx dx plus fy dy. This is minus y dx plus x dy, and we know that this is a very famous integration called dxy, and so the answer will be minus xy. Now the mistake which you may commit is you can many students what they do, they write y dx as yx and x dy, they take x outside and say and they say this is 2x. Now this is big blunder if you do something like this. And now we have to take the limit also. So limit is from 0 0 to xy in general. So 0 0 will give you 0 only. So that's why the answer is still xy. And delta u is u final, which is uxy minus u initial to y 0 0. So uxy minus 10, because this is I have given 10. So the potential at x comma y will be equal to 10 minus x. So in 2 dimension I have given, you can do it for other dimension. Okay, so these are very famous formula, and you can understand that if it is integrable, then only it is conservative. In case if it is not integrable, I mean they will not give you very complex function which you cannot integrate at all. It means it's not like that you cannot integrate is an issue. If something cannot be integrated at all, not because you don't know, because of lack of your knowledge, it's because the mathematics can't do that. It means it must be non-conservative, because conservative force do not need path, non-conservative force need a well-defined path, then you can do the integration over the path, like we did in the last lecture, if you remember the path problem. Okay, so these kind of questions become. The other variety of question that we need to discuss is called equilibrium, types of equilibrium, and conservative force, and so on. The next heading will be for the next lecture, and of course I will not discuss today. It's called types of equilibrium. Now, this is very important concept from the point of view of JEE mains advanced and NEET on examination. So this is I will discuss in the next lecture. Okay, and next lecture will be on Saturday. So hopefully we'll solve the question here. Okay. So now you know almost everything to deal with the chapter. I mean, you can solve any question. That's not an issue, and you can solve all variety of questions also. You know the relationship of potential and force, so you can explore this relation. And the rest I will do, of course, in lectures. So I'll give you all the formal way of knowing things. But the knowledge which we have gained so far is sufficient to solve numericals. Thank you, and I wish you a very happy Diwali
Sir,
to all
one
of you.
doubt.
Yes.
Sir, in NLM, sir, we did one formula that summation of FV cos theta is equal to 0. So what was that? In
Pardon?
energy. Sir, in NLM, we did summation of FV cos theta is equal to 0. So what is
Yeah.
working energy balance?
That was the exactly the work done by the internal constant force, which is zero. That is what I have explained. So tension is the internal constant force. So the tension dot dx, if you add, it is zero. And if you differentiate by time, you can say dx by you can say ds by dt. So this becomes t dot v equals to 0. So anyway, that I'll give you as a power concept. So the power is means we have to discuss the power, which is small topic for JE, but it's a really nice concept to deal with. All right. So we'll see you in the next one on Saturday. Till
Okay, sir.
then, you can have your weekend. So happy Diwali to all of you. Bye.